Okay, if not, let me move on and start with the topic that I want to. This is probably going to be the last topic. Like, if I get some time in the next lecture, I will just give you something about fermions. But the idea today is to talk about a little bit more about the Bose-Einstein condensation. So the idea is to talk about and use this as an example for phase transition. Okay, so phase transition, I would have liked to have covered it, but it's not something we were able to. So what I want to give you in the rest of this course is to just give you a flavor of what a phase transition is, and without going into a lot of detail. Okay, so recall that in the last lecture, we found that if we look at the energy or the number of particles in the continuum limit, then as the temperature goes to, as we lower the temperature, at some temperature Tc, the number of particles, that just like drops precipitously, right? Which is not a physical result. And we found that this unphysical result came from the approximation that we did, where we took the the sum in the partition function and approximated it as a as an integral, and in the density function, the density of state function G of E for the free particle, non-relativistic free particle, there was a square root of E, and therefore we missed the ground state E equals to 0. And if we take into account the ground state, then we get this contradiction is resolved, and we found that, let me just bring up the formula. Yeah. So we found that the number of particle, which we want to have constant, because what we did is that we eliminated the chemical potential. Did we? No, we didn't eliminate the chemical potential, but yeah, if we fixed n, we wanted to keep n fixed, which we can do, and we found that the result that we get from this continuum limit, which is given by, say, v by lambda cubed, and then a function which is called a dilogarithm, and which is a function of the fugacity. And then we found there was an additional contribution from the ground state, which was like this. And the t goes to t naught limit, t goes to tc limit, corresponded to z going to 1. And when z going to 1, we see that this thing blows up, and therefore, as this thing goes down, that we can keep n constant. Okay, so of course, z, this thing blowing up is not something that is physical, and you can now invert this relationship to show that as t goes to 0, and actually as below t equals to tc, fugacity actually it goes to this value where 1 minus 1 over n. Okay, so the fugacity actually takes this value. So fugacity is a weird kind of is a function where, as the temperature goes as the temperature goes down, as the temperature goes to zero, Z actually goes closer and closer to this value. It does not decrease under t equals to Tc. So under t equals to Tc, under Tc, Z doesn't change. Okay, it settles down to this, this thing. Okay, so that's a kind of an important observation. Okay, so now so before we move on to, talk about, so this is basically just a bit of review from before. I don't think I showed this, and this is something that you can just figure out from what we have presented before. So let's now, just before we discuss phase transition, briefly talk about the experimental verification of Bose-Einstein condensation. So the history of Bose-Einstein condensation is the following. So Bose in 1924, sent a paper that had been rejected by 3 journals, I think, to Einstein. So I don't know if you know the story. That's why I'm telling this here. And Einstein really liked the paper. So he liked it so much that he translated it into German and got it published in the top journal of the day, which was called Zeitschrift für Physik. If you translate it, it's called Annals of Physics. And he got it translated. And then in 1925, Einstein worked out the consequences of the new statistics that Bose had discovered, which by now is called Bose-Einstein statistics. And Einstein discovered what we now call Bose-Einstein condensation. Sorry. You guys probably know that, in 1924, when Bose was discovered, Bose-Einstein statistics, he was teaching in Dhaka University, and he was, and he actually discovered it in class. He made a mistake in class, and later he realized that the mistake was not a mistake, and that if you assume that particles are indistinguishable, then it's not a mistake, and that's what led him to discover Bose statistics. Okay, so Einstein discovers Bose-Einstein statistics, and then for many, many years, no one was able to show whether Bose-Einstein statistics, exist in nature. And in 1995, 2 groups, one in Boulder, Colorado, in the US, University of Colorado at Boulder, another one in MIT. So this, the first group consists of Weidman and who was Weidman's, and Cornell. So Eric Cornell and Weidman from Boulder, Colorado, and Wolfgang Kettrel from MIT. They were able to, create Bose-Einstein condensates in the lab and for which they received the Nobel Prize for Physics in 2001. Okay. And what they did is that, they took, systems of bosons, which consisted of like about 10,000 to say 10 million atoms of rubidium or sodium or lithium, and cool them down to incredibly low temperature of 10 to the power minus 7 Kelvin. So this is much colder than the vacuum of space, intergalactic space. As you know that the cosmic microwave background is about 2.7 degree Kelvin, right? So this is a lot smaller than that. So they had to block out everything. So and what they did is that they cooled that down, and they trapped all these atoms in a magnetic trap. So in a magnetic field, and then let go of these atoms. And after letting them go for a little bit, and they measured, after that the atoms have, dispersed to a distance of, say, k h bar by m of t. Then they took a picture, and from that picture they basically got these smudges, and from the density of the smudges, how far they have traveled, they worked out what the velocity distribution was. And velocity distribution, because these are free particles, they basically the momentum distribution, they gave you the energy of the particle. And for t less than t, for t greater than tc, for t greater than tc, they found a much bigger Gaussian, a big Gaussian. So there was a lot of the particles had distribution over a wide range of momenta. But for t less than tc, the hello, sorry, I got cut off because I just lost my electricity. Can you hear me now?
Yes,
Yes,
sir.
sir, we got
Yes,
that.
yes, sir.
Okay. Sorry, I'm joining using my phone. Okay, let me share the screen again. Okay, so for t less than tc, they found that this was a lot more sharp. Now, just a side note that this peak is not at p equals at p equals to 0 because of Heisenberg. Because of Heisenberg uncertainty principle, you can't have a particle which has 0 momentum. Okay, so this will violate the Heisenberg uncertainty principle. So there are some pictures. Let me just share some pictures with you. Can you see? Can you see these pictures?
Yes, sir.
Yes, sir.
So these are the the smudges in physical space. So this picture is for t less than so greater than tc, and we see that for t greater than tc, within that when they actually they do travel quite a bit, but for t less than tc, which are these two pictures, that distance, some of those guys have traveled, but most of them haven't, right? Most of them are still. So this is at t equals to tc, and this is below t equals to tc, and although this length is approximately the same, it's a much more concentrated, and this is the so to speak, the Fourier transform, the momentum distribution, and we see that the momentum distribution below t equals to tc is very, very concentrated. So this is the Bose-Einstein. Uh, you know, um, this is the physical realization of Bose-Einstein condensation.